conservation of energy is very important in physics here. When we look at conservation of energy, it's important to realize that energy is always conserved. There are no exceptions. It's always conserved. It may be transformed into different forms, but it'll always be conserved. Let's take a look at some examples here of how that works. If I had I'm going to make up a roller coaster here and just say, it goes up, something like this. At the beginning here, there's a cart and it has a mass m. And let's say right at the beginning it has v is equal to 0. Okay. Now the nice thing about conservation of energy and all this is that you can choose where you want 0 height. You choose it. And so you know what? I'm going to make this right here, I'm going to make that h equals 0, right at that bottom there. And same with this, that's h equals 0. Okay, and down here is h equals 0. So right down here at the same level, these are all h equals 0. I've chosen that. And in fact, at the beginning here, because v equals 0, that means that the kinetic energy of this object would equal 0 if it's not moving. But what type of energy could it have? Well, it would have potential energy. This is going to have a certain height h. And the potential energy will be mgh. Okay, that will be the gravitational potential energy of this cart at the beginning. It'll have 0 kinetic and mgh for potential. The total mechanical energy of this will always be equal to, the total mechanical energy will always be equal to the kinetic plus the potential at any given moment. So in which case the total mechanical energy at the beginning of this will only be equal to mgh. Now, as this object falls, the potential will be getting less and less and less, but the kinetic will be getting bigger and bigger and bigger and bigger. At the bottom right here, it'll be moving its fastest because the potential energy will be 0, and the kinetic energy will actually be equal to a half mv squared, but will actually be equal to this result at the beginning. So in other words, this mgh will all turn into kinetic energy of a half mv squared. Half mv squared. How about here? This is a little trickier. And what you can see here is that, well, it had all potential, turned into all kinetic. What about here? Here it'll be a mixture of both. It'll have a little bit, I'm going to call that h prime. It'll have a potential energy of mgh prime. But this won't equal the energy at the beginning. And so, some of this will also be kinetic. And I'm going to call that a half, I'll call it k prime, mv prime squared. And so it'll have a mixture of both. Both of these added up have to be the same as what it was at the beginning. It's not gaining anything unless there was external work done. And in fact, this could be less than this value only if there was external work. What could be doing external work? Possibly friction. Friction may be taking away energy this whole time. In order to calculate it, it's a little complicated with this example, but basically you'd have to figure out the force times the distance and how far this thing moved to figure out how much energy was lost due to friction. And you have to take those into account. And so the total mechanical energy can decrease only if there is work done by friction. And of course that's just changing it to other forms of energy. Maybe the tracks get hotter and whatnot. There are other forms of conservation of energy that you can look at. We could look at even a simple example of a spring. And if here's a wall, there's a spring, and I attach a block to this spring, the mass m. If I pull this way, there's going to be a force pulling it back, and it's going to move it. It has a potential to move a distance. Well, let's say that this was pulled back to about here. So here's where it is now. That's where I'm going to move it. So I move it from here to here. It can move a distance, call it x, to equilibrium. It will have a potential energy. What's the potential energy of that? Half kx squared. Suppose I want to know if it started off at this point of v equals 0, how fast is it moving right here? Well, what I would do is say, well, it has a half kx squared at the beginning. That's all going to turn into kinetic. Half mv squared. That should be half mv squared. So all this potential of the spring turns into kinetic. You're going to get scenarios like this, and it's easy to do some of the math because you just need to know several of these factors, and you can solve for the unknown variable, which makes solving laws of conservation of energy problems quite nice. And the other thing is that it actually makes it a little easier in some aspects because you don't have to take into some of the variables that kinematics involve. So energy problems can be easily solved using this principle.